Yanik received bachelor and master degrees in electrical and electronics engineering from Hacettepe University in 2007 and 2010, respectively, and a PhD degree in electrical engineering from the University of Texas at Dallas in 2020. He joined Texas Instruments in 2020, where he is currently a system engineer developing signal processing and machine learning algorithms for mmWave radars. Today, we will gonna talk about target classification on the edge using mmWave radar. Please welcome Dr. Yanik with big applause.
Thank you. Yeah, thank you so much for introduction. So thank you so much also for joining the session. So as you mentioned, actually I'm Muhammet and I'm coming from Texas Instruments Radar Systems and Algorithms Group. And today actually I want to just give a quick talk about our tinyML application using radars, focusing on target classification, and I will give some kind of summary about like our algorithm and how we implement it in our latest IWRS 6432 mmWave radar sensor. So first, actually, I will just talk about like what is mmWave sensing and why we need it, and also why we need target classification specifically, especially on the edge, right? And the other one, I mean, I will just quickly overview about the algorithm that we propose for this application, and what's the novelty of this work that differs from some state of the art. And finally, I will give some short talk about like the real-time implementation of this algorithm running on our tiny device, system-on-chip radar device, which is 6432. And I will quickly overview about like performance results and benchmarks that we actually measured so far. So first of all, like when you call mmWave sensing, you typically refer, radar applications at 60 gigahertz and 70 gigahertz for different applications. I mean, radar has been known, right, for decades, but like due to the technological advances, so basically now we have smaller sizes, especially not just for TI, I mean for also different companies as well, smaller size, lower cost, and high performance system-on-chip devices for these radar applications. So although like the automotive remains a key market for those sensors, so we have a lot of applications, including like building surveillance, factory automation, robotics, which needs some edge processing, which needs like low-cost solutions, low-power solutions to make this kind of end-to-end chains and end-to-end applications running fully on the device. So, and I mean, why we need classification or why we need machine learning, right? So typically, like many traditional radar applications leverage these radar signals for target detection, ranging, or tracking. But as I mentioned, like there are many applications, as I also quickly like discussed in the previous slides, there are many applications needs also machine learning, right? For some applications, you need to understand like gestures. Some applications, you need to understand like the body pose of the persons, and some applications, you need to understand what's going on in the scene, right? And all these applications need basically machine learning. So typically like a lot of nice research is ongoing, right, in especially computer vision domain, and we definitely reuse this kind of frameworks or architectures from the computer vision domain. But there are some fundamental differences between the sensing level, right? The cameras and actually radars has different signal sensing modalities. So this problem needs to be taken care of, especially when you want to reuse this kind of computer vision based machine learning algorithms. So what is this difference? Typically, I mean, if you compare radar with some other sensing modalities like camera, yes, the radars has low spatial resolution, but also at the same time, radar has some unique sensing domains, which is typically like the velocity and range. So in this application, instead of using some spatial domain information, we focused on Doppler information coming from different targets, and as I will show you in a few slides, in a few slides. So basically, if you look at this kind of Doppler reflections, you can see some distinguishable features between different kind of target objects. So, and this work actually focuses on the Doppler information that we received from different targets. So also like the Doppler, micro-Doppler, of course, it's also like a known concept, and there are a lot of research is ongoing in this case. But what we mainly focused is like in a complex realistic environment, how we can generate micro-Doppler from different objects at the same time, right? And how we can utilize them efficiently to make this multi-target classification working for really like the realistic environment, not just for single targets, single objects, with a maybe the cluttered scene with multiple targets around the like moving around, and how we can generate the micro-Doppler from these objects, and how we can just make this classification working. So, and we proposed this solution, and actually like for in radar perspective, what we believe is the machine learning kind of things should be a mixed version of signal processing, like the conventional signal processing techniques, and also machine learning. So you cannot just like provide the ADC raw data and just apply some machine learning techniques to make it working on the edge, especially because there are like huge amount of data, and there are like different kind of scenarios. And what we just proposed here is we typically make this mixed processing chain and end-to-end chain at the So at the first stage, once we get this ADC raw data, we apply the detection algorithms to generate point clouds, and the multi-target tracking actually clusters these points and then make this multi-target tracking work. And after that, when the tracking actually provides some data, then we localize this information for different objects, and we generate the micro-Doppler for each object separately. But there's an important thing also I want to just quickly discuss. If you look at this micro-Doppler, it looks like an image, right? If you just put the Doppler in one domain and time in the other domain, this kind of Doppler time spectrograms can be utilized as an image, can be handled as an image. So some, very nice, machine learning models, some CNN networks, 2D CNN networks can be utilized to understand features and apply this classification working. But here, one way that we believe is, if you want to make this kind of whole architecture simplified, also we applied some signal processing to extract some features with some model-based solution and extract these features and to make this whole machine learning model simplified. So here I will just discuss about like what kind of, and eventually, and once we extracted this kind of features, then we applied some simplified, relatively simplified machine learning models to make this whole classification working for multiple targets simultaneously on these tiny devices. So, I mean, this is like just an overview about the algorithm. Like, as I mentioned, once the point cloud is generated and once the tracker actually generates this multi-target centroids, then we came back to the ADC raw data level and we localize this information and we generate the Doppler information for this track, like around this track, neighborhood. And once we generate this micro Doppler, then we apply this signal processing to extract some features. Just an example here, instead of using the whole image, then we, by using our signal processing accelerators on the device, we generated, okay, what's going on in this, let's say the signature, right? How this kind of signature is changing at this upper side or lower side, or how this kind of whole Doppler is distributed, and what is the spectral entropy, for example. This was another feature that we generated. And once we generated all these features, then eventually we, instead of using the whole image in the classifier, we used a slightly simplified machine learning model that I will also discuss in a few slides to just make this, a machine learning model working. So, but there's one challenge, right, in radar perspective, as you compare it with like the large language models, or like there are a lot of nice works that also other speakers talked about today. But in radar domain, unfortunately, we don't have, a huge amount of data sets to cover a lot of different scenarios so far. There are a lot of nice works actually ongoing in the automotive space, but this is like the data is still limited. So the thing is to just make this whole thing working in many cases, we still needed to apply some signal processing to handle some situations. I mean, there's an example here. For example, think about this. Let's say there's a person, walking around the scene, and it can be, exit from the scene or obscured by some other target. So if you look at the micro-Doppler data, and if you want to directly use this data in your machine learning model, then it will fail, right? Because the thing is, if your machine learning didn't see this kind of certain scenario, then it will not work. And the problem is, yes, we don't have a lot of data to cover all these scenarios. And this is an example corner case, and there are many actually. So for these kind of cases, what we did is we tried to, detect this kind of scenarios and understand this kind of scenarios and apply some signal processing. For example, if we can do just, let's say, interpolate the data, fill these missing samples, and instead of providing this corrupted image into the machine learning model, use this process data with this enhanced information and put this into the machine learning model to just make it working. Because otherwise, as I said, like there are many kind of these scenarios, and you need many kind of data set that covers this kind of cases. Like your machine learning model needs to be trained in that specific case. But this is not the case so far. So now we believe actually some kind of signal processing and some kind of intelligence should be combined with machine learning altogether to just make this kind of scenarios working, especially in the radar domain. So that was the one more thing actually we just added to the processing chain. And eventually we came up this simplified model. It's like a simple model. And if you think it's just a 1D CNN based model with utilizing as a baseline 2 blocks of 1D convolution and ReLU and normalization layer, and we also added another layer here to just make this make it comparable and to just enhance the performance with some overhead, of course. But each layer has like different kind of filters, and eventually everything is just followed by a 1D global average pooling layer and a fully connected layer, and followed by a soapmax layer. So the thing is, we had to implement this model in our tiny device, and I will just quickly discuss about what this device is. But typically it has like an ARM M4F core, and when we benchmark this model on this ARM M4F core with 2 layers, it took about like 3 millisecond processing, and with additional layer it took about like 15 milliseconds. The problem is actually you can make this model complicated, and these benchmark numbers can be higher, but the thing is you may have multiple targets, right? Maybe in some sense you may have 10 tracks, and you need to classify these 10 tracks simultaneously, so everything is just like 10 times increased. So the thing is we really wanted to make it much more simplified, and we just came up with, let's say, 3 millisecond or 15 millisecond processing time to make the whole thing working at 10 hertz. So, and in terms of memory, we are just talking about like less than 50 kilobyte of memory, memory footprint for this simplified model. So, and the thing is, so to just train this model, we created, we had to capture our own data. So we created like 300 different scenarios from 3 different human and numerous non-human targets. And we generated like, we almost like captured about like 3.5 hours of data. And once we captured the ADC raw data, we run the whole signal processing chain, including detection, tracking, and once we generate the microdoppler, we labeled this data, we extracted these 4 features, and then we, trained this model. And finally, we achieved actually this kind of performance accuracy. So to just actually understand the the performance, we needed to make this model as robust as possible. So we tried different options. Once we captured this whole amount of data in the first approach, we reserved the 50% of data for testing, and for 2 milliseconds window size, we could achieve around like 94% of accuracy. But of course, like if you accumulate more data across time, if you increase your timing window from 2 seconds to 3 seconds, your performance can increase that, but the trade-off will be more latency. So now you need to buffer more data to make this classification working, which means like you will need more latency. But in the other approach, of course, like as in any other typical machine learning papers, so we basically reserved some certain scenarios, let's say some certain people, some certain scenarios, we completely reserved them. And then we trained this network with the remaining data, and we could also achieve a similar amount of performance. And also, the one more thing is, once you generate the microdoppler, right, instead of getting this microdoppler information from a single point of the target, if you just get this microdoppler information from a certain boundary, then you will get better microdoppler signatures, because think about this, we are not like rigid bodies, right? We are walking, and we have different parts of our bodies, like arms, legs, and if you accumulate more information from different points, which we did here, and eventually you can get much more distinguishable signatures, and much better performance metrics. So this was the performance results we saw, and I just wanna, I don't know how much, how much time we have, I don't know, but yeah, let me make it quick. So, so the device that we focused on this application is like our latest IWRS6432 device, which is cost and power optimized radar on chip with both analog and digital processing combined on a single device. So that device has 3 RXs and 2 TXs and an ARM Cortex M4F processing core and hardware accelerator, which is responsible for some certain signal processing blocks. And eventually the whole device has a 1 megabyte of total memory. And we wanted to, run this algorithm fully on this device in real time. So the thing is, I mean, in TI, we are not like fully interested in the final product, but instead we are interested in building blocks, right? We develop these building blocks, and people can take it and they can just combine them and utilize them and maybe leverage them to implement this chip on their final product. So here, what we did is like for every processing block that I just mentioned in the previous slides, we created them, we implemented them as a data processing units with well-defined ABIs, including detection, tracking, microdoppler generation, and everything. So everything is just architected in this way. And as I said, like with well-defined APIs, different models can be injected here, or maybe some of the processing blocks can be enhanced, and these kind of things. And one important thing is to just make this whole working real time with this tiny device. We parallelized everything, everything that we can. For example, we have a CPU ARM core and a hardware accelerator. So we parallelized the processing blocks at each DPU to make this implementation as efficient as possible. Also, as discussed in some of the previous slides, the data movement is also an important bottleneck, and we have a huge data set coming from the radar RF units, and this data needs to be moved around for every block. Once you run something, you just need to move this data very efficiently. And in this device also we have the 64 different EDMA channels, and we highly parallelize this work by using this EDMA channels as efficient as possible. And eventually our whole processing from ADC sampling to the final decision takes about 35 milliseconds for 3 tracks, and each track also adds just 3 milliseconds of additional processing. So we targeted for this application for 10 hertz, but also we can go 20 hertz of processing. And in terms of power consumption, at 10 hertz, we are talking about 50 milliwatts or 60 milliwatt power based on the chirp configuration, of course, but we are talking about 60 milliwatts, I mean, much less than 100 milliwatt power consumption. So now the EVM, the device EVM, is available on ti.com, and also we packed everything in our latest SDK framework. And if you check out this SDK framework, you will see this whole, to make this device running, you will see all the low-level drivers and RTOS and all kind of, data processing units for each block, which is already available with all the source code, and the whole demo application, which is running all these processing blocks to make this final classification showed up, and it's also available in this latest SDK released. So this demo actually, this is just showing, a simplified example to just make it, visually understandable. Now you will see that if there are multiple tracks in the scene, it doesn't matter how many tracks you have. I just make it simplified here for 1 track, but it's also working for up to 4 or 5 tracks. So whenever the track is moving different, in different cases, every data is localized in that centroid, and the microdoppler information is generated. And this microdoppler information is distinguishable. This is a simple, non-human object, but if you see different kind of things like trees or plants or fans or pets, now you see different kind of microdoppler signatures, and this make the whole framework working. So one thing is also we found that this microdoppler signature is also important for maybe other use cases as well. Let's say fault detection or pose estimation. This kind of microdoppler signatures, they are already streamed out from the device, and this kind of data can be also reutilized, to generate or to build different kind of machine learning models as well. And this is just a summary slide, and this example actually shows how the overall structure works. Let's say you have two different objects here, like fans. Let's say a human is walking, and the data, like the point cloud, is generated. The tracker is tracked, actually, every track separately, and eventually all this microdoppler is generated, classifier runnings, and it finally classified as human, non-human. And using this multi-target tracker integration and robust microdoppler generation, and basically we made this multi-target classifier running on this latest 6432 device as efficient as possible. So, so actually, yeah, this is the end of my slide. Sorry, I hope I made it on time.